Okay. So Wilson, please start your presentation. Thank you.
Okay, Kai, thank you very much. I'm very pleased with this opportunity to share our latest finding with everybody. Now, I called this title as using interharmonic power for power system oscillation source location. So this is basically derived from our voltage flicker investigation presented in November 24. So I want to present this in following 5 topics. First, I give you some background from voltage flicker research to voltage oscillation research, why I moved from power quality to this stability subject. Then we'll talk about the findings. Basically, 3 main findings. One is the relationship between interharmonics and phasor oscillation. Another one is the interharmonic power can be used for source location. There are also additional interesting findings I want to share with you. Finally, I want to identify some future research needs. Now, for the background of this presentation, last time in November last year, we presented this case for a voltage flicker case. That is really, we found this area experience voltage flicker. Now we measured the waveform here. We find that the fluctuating waveforms. And we conducted spectrum analysis, find the interharmonic components and in the waveform. So this is basically for this particular operating condition, we found the interharmonics around 117 Hertz, 237 Hertz. This is the enlarged portion of this area. So basically, this type of spectrum components have definitions by IEEE standard, which basically shows that interharmonics are spectrum components whose frequencies are residing between harmonics. In this presentation, or in all my work, I don't differentiate spectrum components that are below or above F1. I call everything as interharmonic components, just for the sake of convenience. Some people call spectrum components below fundamental frequency as a subharmonics. In here, subharmonics are also called interharmonics. Okay, so in this particular investigation, we used the direction of the interharmonic active power to locate the sources. This has been located successfully, and the industry actually made changes to the filter and solved the problem. Later I will show you the mechanism of interharmonic generation from this case. So this work was done actually 20 years ago. So in 2018, I visited Denmark, attended several presentations. Then the industry showed the wind farm and waveforms. It's something like this. At that time, I started to realize this is very similar to the voltage flicker waveform I have seen before. So it's possible to also investigate as the interharmonic phenomena here. But it takes about 6 years for us to figure out what is the best way to investigate this, to convince the stability and the phasor researchers that interharmonic indeed play a major role in this type of waveforms. So basically, finally, we have published, get the work done published. So basically, this is the latest thinking to convince the stability researcher. First, we have to prove the existence of interharmonics is the necessary and sufficient condition for any phasor oscillations. Secondly, we have to show synchronous generator oscillation can be explained using interharmonics. We also need to demonstrate IBR oscillations are also caused by interharmonics. So finally, we must use convincing field measurement data to support the above claims. So we have spent 1 year to collect the data, especially the synchronous generator data. So finally, we have everything together now, and I want to share it with you. today in this presentation. Okay, first is to establish the relationship between interharmonics and phasor oscillation. So the paper has one theorem, that is the existence of interharmonic components is the necessary and sufficient condition of phasor oscillation. This diagram was presented in November presentation. It's very important. I want to show that again. So basically, let's look at voltage waveform, which consists of fundamental frequency component and an interharmonic component. If you plot the waveform together, you add them together, you can see this beating wave phenomena. The beating is caused by that interharmonic peaks values are not synchronized with the fundamental frequency component. Like in this window, and the waveform of the two interharmonic and fundamental subtract each other. In this window, they're adding together. Therefore, and you have a large magnitude. Here you have a small magnitude. When you do phasor calculation, phasor formula is this. Every cycle you compute a value, which is a phasor, which is essentially you compute the RMS value of this waveform versus this waveform. You can see the phasor values will be less in this case, and the phasor value will be high. So basically, this demonstrated that interharmonics is the sufficient condition to cause phasor oscillation or to cause beating waveform. Actually, beating waveform is very well known in many waveform domain. Now, and the paper also showed that this is interharmonics are necessary. It is you need the interharmonics to cause phasor oscillation. If you don't have interharmonics, the phasor will not oscillate. This second part of the necessary condition proof is shown in the paper, so I don't want to waste everybody's time to explain that. Now, so the important takeaway is the following. So oscillation is the appearance of a waveform beating pattern in the phasor domain. The beating pattern is actually formed by interharmonics interacting with the fundamental frequency wave. Therefore, the presence of interharmonic is the general cause of phasor oscillation. I wanted to clarify what I mean by general cause. And is that each oscillation has a specific mechanism, specific causes like mechanical vibration. However, no matter what is the physical cause, all events manifest as a beating voltage and current waveforms from the electrical signal perspective. So the beating waveforms are in turn caused by existence of interharmonic components. This interpretation applies to all type of phasor oscillation phenomena, regardless of the physical mechanisms. So basically, we are not approaching the phenomena by looking into the physical mechanism. Either are you inverter caused or you rotor oscillation caused. We basically from electrical side, that is what we see. This generalization can be very helpful to find a general method for source location, for example. Now, and the second evidence is the synchronous machine oscillation. We can use interharmonic to explain this very well. So first, this is common. We see that hypothetically we have 11 hertz phasor oscillation observed at a synchronous machine terminal, the voltage. Now, if you look at the waveform, it's basically a beating waveform. If you do the spectrum analysis, you will get 3 components in the state of voltage: 49 hertz, 60 hertz, 71 hertz. Now, this basically representing a 3 rotating magnetic field in the stator surface. So 60 hertz component have a synchronous rotating magnetic field. 49 hertz is rotating at this speed, basically at 49 hertz. Now 71 hertz also rotate. We can prove mathematically that are in positive sequence, so they rotate in the same direction as the rotor direction. Of particular interest is the 49 hertz magnetic field. So we look here, 49 hertz, we have 60 hertz rotating stator. So basically, the stator, 60 hertz rotating field of the rotor rotating at 60 hertz. So basically, we have a stator magnetic field rotating slower than the rotor magnetic field. This is essentially an induction generator effect. Okay, so here, if we can look into the induction generator curves. So, and this part is the motor characteristics. If the stator magnetic field is faster than the rotor, is slower than the rotor, we have a negative slip. Now this basically, we have an induction generator effect if you are recall machine. So the simplest way to understand this is to compute the equivalent circuit of this phenomenon. So we use that stator 49 Hertz as a reference point. So we have the rotor rotating at 60 Hertz. You do the calculation, you find the slip is negative. Therefore, you have a negative resistance in the equivalent circuit at this particular frequency. Therefore, 49 Hertz power is produced by this negative resistance. So this is how I explain the interharmonic and cause synchronous generator oscillation. So the grid could have a variety of disturbances like caused by switching event. So a disturbance introduces various spectrum components in voltage current. Now one spectrum component, for example, could be 49 Hertz. Now this component causes multiple synchronous generators to produce power at 49 Hertz, like an induction generator. This power enters the grid. If it cannot be consumed by the grid, for example, and because resonance amplifies this component, then it will set up increasingly higher 49 Hertz voltage and current in the system. This positive feedback loop results in the oscillatory instability of the generator and the grid. So this is how interharmonic can be used to explain synchronous machine oscillation. So the paper has also two other examples to illustrate the synchronous machine does generate interharmonics. Now, and how about the inverter? So there is another theorem in the paper shows the generation of interharmonic power is the necessary condition of small signal instability of IBR and the synchronous generator systems. So here is the mathematical treatment. Basically, we have a grid. You can model grid as an impedance model or a transfer function model. This is essentially transfer function model. Then IBR or a synchronous generator, I call this generator as another model. You connect them. Now this can be converted into a feedback model using the standard control system model. So there is a theorem in the control system shows that for this system to be stable, both H1 and H2 has to be passive. So that means for this system to be unstable, one of them must be non-passive. That's what this is, small signal stability. Now, and at the frequency, this is non-passive, which is typically interharmonic frequency. Then you generate interharmonic power. Then that's why interharmonic power is also involved in the inverter-based circuit. So here is an interpretation of this phenomenon. So we have on the grid, we have an inverter. The PLL senses the grid frequency, then initiate PWM switching to produce power at this frequency. Let's see, suppose grid is running 60 Hertz, experience a disturbance, then PLL detect, because some transients in the waveform detect as a 60.5 Hertz grid frequency instead. Then the PLL will let the inverter inject this frequency into the grid. Then this interharmonic is amplified because high grid impedance. Then the PLL will see a different frequency because the waveform is distorted even more. So eventually this process reaches a kind of steady state at a 74 Hertz PLL frequency, leading to a 14 Hertz of sustained or increased phasor oscillation. So this is a kind of explanation of this phenomenon. Now, there is another way to demonstrate the evidence. So, we have basically a grid. And we each and IBR or SG is impedance model or transfer state equation model. Now you can develop a system dynamic model, either in the state space or in a transfer function form. I want to emphasize this must be EMT type of model. What I mean by EMT type of model is basically waveform-based model, which is basically the capacitor has to be modeled as a transfer function. The inductor modeled as transfer function. This model is widely used in power electronics and also used for subsynchronous resonance analysis because the frequency is so different with 60 Hertz. So this has to be taken into account. Now this model, you have an eigenvalue developed. You can find an eigenvalue for this model. Now this particular eigenvalue, for example, kth eigenvalue, you have a frequency omega k. This omega k is basically 2 pi fk here. This is essentially interharmonic frequency. So basically, stability researchers already know where the system eigenvalues have frequencies. These frequencies are the interharmonic frequencies we are talking about here. Okay, now and you may have read some papers, people claim this is harmonic instability. This is total exaggeration, and this is nothing new here, this phenomenon. It's just a small signal stability in the waveform domain. So it's no point to call this as harmonic instability or even interharmonic instability. This is just a small signal stability phenomenon with different oscillation frequencies. Okay, so we have 4 evidence provided here. I hope this is convincing enough for phasor or stability researchers to agree that interharmonic can play a role here. Now, and next, I will talk about the interharmonic power-based method for source location and share with you the field measurement results. Now, and the logic of this method is very simple, intuitively clear. Oscillation means that beating voltage current waveforms. Beating waveforms are caused by interharmonic voltage and current. Powers are needed at this particular interharmonic frequencies to drive the propagation of interharmonic voltage current in the system. So therefore, it is reasonable to call interharmonic power producing components as sources causing oscillation. Now we can check the amount of interharmonic power produced by various components. We can locate oscillation sources and rank the impact based on the amount of interharmonic power produced. So the implementation is very simple. Here I just show you the simplest interpretation and implementation. Basically, we perform DFT on the voltage current waveform data of monitor. Oh, by the way, this is the setup. So we have a grid. We monitor each power plant with this monitors here. You can monitor load facilities too, if you want. In fact, most of the power plants have power quality monitor, can monitor, or your other monitors can monitor waveform already. So, and then what we do is once you get the waveform, trigger the recording of oscillating waveforms or your beating waveforms, then you do DFT using moving window, then you extract the key interharmonic components, then calculate the 3-phase interharmonic active powers generated, 1 data window by 1 data window. Then you can compute the average powers or your accumulated energy, which are essentially the same. Okay, over the period of interest, then you compare the interharmonic powers for the same period, then rank the sources. So the networked monitors are actually available already. For example, power quality monitors can actually record interharmonics, but the current recording practice is based on IEEE standard. So the software needs to be modified for this kind of specific task to compute interharmonic power. Then we can also monitor key interties to determine if the particular oscillation is a local oscillation or your system-wide oscillation by correlating the event starting date time and the ending time with the locally recorded interharmonic results. Okay, here are the for and field measurement cases. First is a synchronous generator. For this particular synchronous generator, if the voltage goes below to certain value, it has started to oscillate because of poor controller's exciter setting. Here is the recorded voltage waveform. Okay, and I only show the top part because the oscillation is small, but the current oscillation is very noticeable. If you perform spectrum analysis, you will see that there are two interharmonic components here. So the current part is more visible. One is 52.58 hertz, one is 62 hertz. Now, if you compute the interharmonic power, you can see that positive means generation. So therefore, this interharmonic power is indeed generated. This interharmonic power is modal. It has a modal effect, okay, which is equivalent to the 71 hertz I showed you earlier, which is a modeling effect. Now we observed the trend of this pattern is very interesting, something surprising to me. You see that what we recorded is a moving window computed the fundamental frequency power and the phasor power. Phasor power is computed by phasor voltage multiplied by phasor current times the power factor, right? So we also computed the total power. Basically, total power according to Fourier theory or energy conservation theory is basically instant power integration over the period of oscillation. So you have a spectrum components. Basically, those which each one has different frequencies. For example, interharmonic frequency is here. So you compute each component. This is what we have computed: 58 hertz interharmonic power, 62 hertz interharmonic power. Integration of this, you get a positive energy output. So you basically inject the interharmonic power to the grid. The most interesting part is that we see that the phasor power oscillate, but the actual 60 hertz power don't oscillate. So I had always had the impression the phasor power is supposed to represent 60 hertz power. Actually, this is not the case. So that means the oscillation is actually a beating phenomenon caused by the interharmonics become theorem 1. Now, why this interharmonic power oscillate is more there is more detailed analysis in the paper. I don't want to waste time to explain this phenomenon. Okay, so the next case is wind farms. We are able to get data from two wind farms. When this circuit breaker opens, then there is a large grid impedance connected to wind farm. Both wind farms started to oscillate. By the way, this wind farm data 1 is also recorded, but it is incomplete. So we cannot do analysis on wind farm 1. Okay, so we have this two wind farm 2 and wind farm 3 data here. You can see that they also have a key interharmonic component around 54 hertz. 64 hertz. Then the interharmonic power is computed. So basically, wind farm 2 has generated more interharmonic powers, so which is the dominant source compared to the wind farm 3. Okay, so now the interesting part again is to see the pattern. In this case, the phasor power oscillate, the 60 hertz power don't oscillate. Same thing here for the other wind farm. Now we also looked at the currents, interharmonic currents and the phasor current, 60 hertz current, interharmonic current. You see the phasor current oscillator. This is basically a beating phenomenon I explained earlier. Now this is the 60 hertz current. It's a steady state. Now interharmonic current doesn't oscillate. Interharmonic current added with the 60 current cause beating waveform. Then the phasor interpreted the beating as an oscillating phasor, basically. So this is the same phenomena observed. This is very interesting. I'm still spending time to try to understand what is the actual phenomena involved here. What is the implication? So my preliminary explanation is the following. Phasor is a human-created concept. So You multiply voltage current phasor, you get this oscillating phasor power. But this doesn't necessarily represent what is experienced by actual system elements, R, L, and C here. Such elements actually determine system behavior. The system behavior happens to be steady state 60 Hz of power. Okay, I need to spend more time to figure out this. Okay, the third case is a solo form. We have basically, when a capacitor is energized, it's set up a resonance at a certain frequency. I think it is the interharmonic frequency. Therefore, this solo form started to oscillate. Here is the capacitor switching. Then you can see the oscillation of the current. The voltage also distorted. Now you can find that there is a 84 Hz interharmonics here. So you get the interharmonic power injecting to the grid. Clearly, the solo form is the oscillating source injecting. Number 4 case is the voltage flicker case. I have presented in the last presentation at the beginning of this. I wanted to use this opportunity to explain why we have interharmonics in the VFD. Basically, this is the system, the pumping station. It has several filters connected. This is a variable frequency drive here. So if you look into the impedance of the filter combined with the grid, you get this impedance pattern. You can see there is a resonance point here. Now, and the VFD actually can produce interharmonics through this mechanism. We have converter 60 Hz into DC. DC then through inverter converted into a variable frequency. For example, 43 Hz. This system is actually bidirectional. You can imagine this motor produces 43 Hz and the signal. Then you have a 43 Hz ripple here. Ripple penetrated to the grid becomes interharmonic. So therefore, and the interharmonic frequency is a function of the drive speed, basically 43 Hz motor frequency. So, and that's why we have this interharmonic or oscillation phenomena. So the interharmonic changes with the drive speed. When the drive speed hits this resonance point, we see huge interharmonic, and the voltage flicker is produced. So at the end, the solution is to modify the filter to avoid a resonance at this frequency range. This is interharmonic power produced by the drive. You can see that the resonance is actually for this particular operating condition. It is this one, 237 Hz hit resonance higher. Okay. So basically, to summarize the findings here, it makes sense to use interharmonic power as an oscillation source locator, which is based on law of energy conservation. The interharmonic power can be determined using DFT analysis. The method can be easily implemented based on based on power quality monitoring experiences. We have used 4 field measurement cases to demonstrate that interharmonics are indeed involved in oscillations. The interharmonic power-based method can locate sources. Now, there are some additional interesting findings I want to share with you. First is that let's clarify 3 frequencies. One is frequency of phasor oscillation, FOS. Another one is the frequency of the eigenvalue or the pole, F pole here. Then there is the frequency of interharmonic, FIH. Basically, this is the eigenvalue plot of the EMT model. As I showed you before, this is the frequency of eigenvalue. So basically, frequency of eigenvalue is interharmonic frequency. So this is the frequency of the interfering wave. This frequency interferes with the 60 Hz wave, create a beating pattern. The frequency of phasor oscillation is actually the frequency of beating. That's the beating frequency. There is a formula developed in the paper to show that the oscillation frequency is related to the eigenvalue frequency or your interharmonic frequency. So with this formula, this H is the harmonic frequency closest to the pole, to the interharmonic frequency. From this, we can find this interharmonic versus phasor oscillation curve. Here, I want only spend time to explain the frequency part, this right-hand axis. Here is the interharmonic frequency. Then here is the phasor frequency. oscillation frequency, you can see that maximum oscillation frequency is 30 Hertz. This is why we haven't seen oscillation above 30 Hertz yet and reported in the field. This is not because the phenomena doesn't exist, because the phasor can only report up to 30 Hertz frequency based on this analysis. Why this is the case? This is like similar to the Nyquist sampling theorem. Basically, phasor is defined for each cycle. So that means in 1 second, we only have 60 data output for the phasor, 60 data points per second. So therefore, we are essentially sampling a 1 cycle data, 1 second data using 60 samples. Therefore, the highest reporting frequency is 30 Hertz, similar to the Nyquist sampling theorem. That's why, and we have this maximum 30 Hertz reporting. Another phenomenon interesting is that you have here, you definitely have two interharmonic frequencies different. However, you have the same oscillation frequency. So that's why the phasor is hard to decipher which interharmonics are actually producing this oscillation frequency. Another interesting finding is the following. Okay, the interharmonic power relationship with eigensensitivity. Here is we can develop a system domain dynamic model here, which has an eigenvalue as shown here. So for example, IBR or SG, you can model as a transfer function as an impedance model. That is the real part, imaginary part. If you vary the imaginary part, real part, you do a very little change, small change, you get eigensensitivity. The eigenvalue will move, right? This is eigensensitivity is the sensitivity of eigenvalue as divided by the variation of the conductance of the impedance model. What we find is that eigenvalue sensitivity is proportional to the interharmonic active power of this particular generator. Therefore, measuring interharmonic power is equivalent to measuring the model of your eigenvalue sensitivity. This is a very interesting finding from this research. And this finding also provides a theoretical support to the use of interharmonic power for source location. This source interharmonic power for source location intuitively makes sense, but here we provide a theoretical support. Okay. Another finding is that we want to know which components cause resonance, which in turn leads to oscillation. For example, in this setup, we know the capacitor causes resonance, but these are inductors, which inductor participate in the resonance even more. Okay, so oscillation is associated with resonance, and larger resonance causes more noticeable oscillation basically. Therefore, we know that resonance is associated with energy exchange between reactive power components. Therefore, basically, the idea is that we can use interharmonic reactive power to identify rank these components to see which components actually contribute to resonance. So, we can prove mathematically. For example, you have a capacitor here. When you vary the capacitor suspense B, then you have an eigenvalue will move. There is an eigenvalue sensitivity. We found that the eigenvalue sensitivity is proportional to interharmonic reactive power. Therefore, there is a theoretical support to use interharmonic reactive power to identify and rank resonant components. This can also become implemented in the power system monitoring. Another thing is that, there are two types of tools for power system stability, small signal stability studies. This is focused on the study part, not the monitoring. But the monitoring idea helped this idea. So we have EMT simulation. Basically, engineers use two tools. One is EMT simulation like PSCAD, widely used, but it does not offer stability characteristics of the system, such as participation factors or critical generators. Another tool is eigenanalysis, is a state matrix based or impedance matrix based. It can offer participation factors, but you need to run a new tool. Basically, eigenanalysis tool is needed. Okay, based on this research, we found a very interesting and efficient efficient approach. Basically, for efficient stability studies, basically we perform EMT simulation for a system use PSCAD, for example, as usual, because EMT simulation is more widely used. Then we can measure the interharmonic active power from the simulated results. Then you get a generator participation factor. Then you measure the interharmonic reactive power from simulated results. Then you get a resonance participation factor. Then therefore, there is no need to use eigenanalysis tool for practical engineering studies. When I was in BC Hydro, I do this type of studies all the time. So it is quite inconvenient. You use two tools. And also, eigenanalysis, basically the value is a participation factor. I don't need to know how many eigenvalues are in a different location. I only want to know the critical eigenvalue, then what are the factors. By doing this EMT simulation, I can find the participation factors already. Then I don't have to do these studies. So, and I do EMT simulation. Then I use this participation factor to explain my EMT result. Okay. So basically summarize and research needs. So the key point is takeaway is the following. The propagation interharmonics in a system is the general cause of power system oscillations. Interharmonic power needs power to drive the propagation. Therefore, we can use interharmonic active power for source location. Then we can also use interharmonic reactive power to detect resonant components in the system. This measurement-based concept can be extended to simulation. And then we can support simulation-based power system studies. And another interesting finding I want to share with you is the following. You see that entire concept here. We have oscillation phasors. Then we use a Fourier transform on the waveform. We got interharmonic components. It give us new insights, a new way to understand oscillation. Okay, such as actual rotating fields and in the air gap for synchronous machine. There is a parallel here. When we have unbalanced phasors, we use a symmetric components transformation. We get a sequence components. Then we have a new way to understand unbalance. We have, for example, have positive, negative rotating magnetic field in the gap for synchronous machine. Then we develop different methods for unbalanced analysis. So for this new approach, we can develop a number of methods here, like a source location, which has been developed. We can develop a stability analysis and participation factors. Now, how about the interharmonic relay, interharmonic stabilizer, etc.? Okay, there are lots of opportunities to innovate. Now, and the follow-up research is immediate, is for oscillation source location, like a more accurate interharmonic determination, such as window size, window shape, spectrum leakage, minimize spectrum leakage, etc. Interharmonic distortion determination for non-stationary, basically short duration oscillation waveforms. And for me, I really want to understand the SG and the IBR behavior, and especially the phasor behavior from the interharmonic perspective. Immediate future restricted need is like use YS matrix-based stability analysis, such as characterize the propagation and the coherency of oscillation, use the participation factors. Now, interharmonic relay, maybe for load shedding, for generation shedding. Now, can we use active interharmonic filter or active interharmonic energy observer to damp power system oscillation? Okay, basically that's my presentation, and you can find more information from this paper. Thank you. Yeah. Mhm.